Well, hello and welcome back to Engineering 201 Electrical Fundamentals, and I want to start a new section. We have a couple big sections left in this chapter before the end of the term, one of them being Transient Analysis, what we're going to start today, and the last being Introduction to AC, which will be introduction to essentially what we're going to do most of next term. So, with transient analysis, we're going to look at RC circuits, so the analysis of RC circuits, resistor and capacitor circuits, and RL circuits, resistor and inductor circuits. And one of the requirements is that we have only one energy storage element. So in fact, if it's an RC circuit with multiple capacitors, if we cannot combine all of those capacitors into one capacitor, we're actually not going to be able to do that. So we're fairly limited. It is going to have to be resistor capacitor circuits, or resistor inductor. And in fact, because I can only have one energy storage element, we could not do RCL circuits. Your textbook will talk about RCL circuits, but since we're on a term system and whatnot, we're not going to do that this term. We'll come back third term for the electrical engineering students and talk about a method where we can look at these in a little different light, and we'll come back and look at problems like that. So anyway, with transient analysis, I want to start with the equation, the differential equation here, that dx of t dt plus a x of t is equal to some function of time f of t. And I realize full well that most students are not in differential equations. If you have taken differential equations, you can probably appreciate that equation. But pretty soon we're going to wrap this all up and put it in a nice tidy black box and come up with a 6-step method that it won't matter whether you've been through differential equations or not. But I want you to have a little appreciation for what goes into that black box, and maybe some motivation for when you're studying this in a term or two, that you can have that aha moment where you say, oh, well, that kind of an equation pops up in electrical, that's why I need to know this, and so forth. So with this differential equation, fairly general differential equation, it has a solution where x of t would be equal to x of p, what we call the particular solution, x of p of t. And this is actually, another name for this is the forced solution. The forced solution, because we have a forcing function there. And we could further say, if we looked at this equation here, similar equation but with a big difference, this one I'm going to set equal to 0, so in fancy math terms that would be homogeneous. It's not, doesn't have a forcing function, it's a homogeneous, it's set equal to 0. And it has a solution that looks like this, where x of t would be equal to, we'll say that this is x sub c, the complementary, sometimes we use complementary. And sometimes we'll talk about this, while this is forced, this is the natural. Okay. So then any reasonable solution would include both of these, that x of t is going to be equal to the particular solution plus the complementary solution. Okay. So that's generally where we started. We're going to do a few things here. What I'd like to say is that we're going to look at f of t as a constant. So if this is a constant, I could say then that this differential equation and maybe I'll put the p in there, the particular solution, a x p of t is equal to a. Okay, that's the constant that we've got there. And double check that. I think we're okay. Double check a couple things here for sure. Sure, not propagating a mistake through this. No, I think we're good. And then the other equation, we'll always have this pair of equations here, dx sub c, the complementary solution, plus axc of t is equal to 0. So we've got those two. Let me get a different piece of paper here. And we can say that if A is a constant, then the particular solution is a constant. Okay, so back over here, if that's a constant, then our particular solution is going to be a constant. And we can see that. We'll let me set xp of t equal to, we'll say, k1. That's our constant that we're going to use for that. And if that's equal to a constant, d then xp of t dt is equal to 0, right? So we come back over here. If this one is equal to 0, then I'm just looking at that. So I've got a k1, that was our substitution there, is equal to the constant a, or that the particular solution is equal to k1, which is equal to a, the constant, divided by a lowercase a, and we'll address that, what that is, in just a little bit. But let me go look at this. We've talked now some about this one. Let me go look at the homogeneous case. So also note that the derivative of the complementary solution is going to be equal to, rearranging this equation, we take that over, so we get minus a x sub c of t, and then when I divide both sides by xc of t, then I'm just left with negative a on the right hand side, so I'd have minus a. So I could rearrange this further. Maybe I'll use some space over here and say then, rewriting this a little differently, I have the derivative with respect to time of let's see, derivative with respect to time. What am I going to have? Yeah, this would be the log xc of t is equal to minus a, right? And we go back, what's the derivative of the log of u? What's that equal to? Du over u. So when I take the derivative of this, I get back to that, the derivative of the argument of the log divided by the argument of the log. So this is just in general. In general, we've got that. So if I take this then and integrate both sides, so integrating both sides, I have the natural logarithm of the complementary solution is equal to minus a t plus then the constant of integration, right? So I'll pick up with that on another sheet here. So I can say with that over here that I've got the natural log. I'll just rewrite this so it gets over here. The natural log of the complementary solution is equal to minus a t plus our constant of integration. And what can we do with that? I could say take e to both sides, use e to get rid of the natural logarithm, right? Okay, so I've got then the complementary solution here is equal to e to the minus at plus, so that would be a multiplied by, wouldn't it? E to some constant. Okay, I believe that's how the algebra works on that. And I could do a bit more rearranging here. The complementary is equal to this e to some constant. That's just going to be another constant. So let me say that let me say that that's K2. And then I'll have e to the minus at. So I've just said that this is a constant, K2. So now I've got a form for x sub c. I had a form for x sub p, and I can put this together. We know that, remember that x sub t was equal to the particular solution plus the complementary solution, which our particular solution, that was a over, that was right there, wasn't it? Capital A over lowercase a plus K2 e to the minus, using this one up here, K2 e to the minus a t. And I could really say that that was, I mean, if I wanted to, this was this was actually K1, wasn't it? So I could write this as K1 plus K2 e to the minus a t. That's what the solution form looks like. So then the task is to figure out what K1 is, what K2 is, and what a is. Okay. A few things about this. We could say that back here, and why I wrote this as a over a, this is defined as our steady state solution. So we have the transient situation, where transient is going to be a function of time. We move a switch and we look at what's happening to voltage or current somewhere in a circuit. And as time gets longer and longer and longer and approaches infinity, we talk about the steady state solution. That's what that is. Okay? That's when the time goes to infinity. Okay? And I'll talk about time constant and come back to that in just a second. Speaking of time constant, that's the time constant is going to be equal to 1 over a. So that's defined as the time constant. And a lot of times we get a little nervous when we talk about time going to infinity. We don't have that long to wait around. We get a pretty good answer when the time is equal to or greater than or equal to 5 times the time constant. We'll look at some examples of that. Well, what's this solution look like? It's probably worth looking at maybe a graph. So I'm going to come over and graph this thing. And probably, maybe I can get that on this sheet. Yeah, I'll leave it here so it's nice and large. So if I have a graph here with time on the horizontal, and I'm going to put my function over here. So I'm going to talk about K2 e to the minus t. We had what, minus, so looking at, we've got the steady state solution here. That's going to be a fixed value, and then this one's going to be changing. This is a function of time, right? Okay, so I've got minus a. Minus a was or a is 1 over the time constant. So I have t over the time constant, right? This last term here essentially turns into K2 e to the minus t over the time constant. So let's look at graphing that one. I mean, this one's a constant, not very exciting. This one's going to be doing something. So let's see what that looks like. So I got K2 minus t over the time constant. And when t is equal to 0, I have just K2, don't I? All of this business over here turns to 1, doesn't it? And I'm going to get a exponential decay. It's going to do something like that. And it's kind of interesting. There is a point here at 1 time constant. And I know at 1 time constant that this has to be equal to 0.368 K2. Okay? And sometimes students wonder, how is that? Where we have here 36.8%. Did I get that right? Yeah. 36.8%. And here is, what, 63.2%? Well, where in the world does that come from? Well, let's go back and look at our expression. K, or K2, e to the minus t over the time constant. And we're going to let t equal 1 time constant. Okay, so if I do that, then I can say that we have K2 e to the minus 1, right? And e to the minus 1 turns out to be equal to, so I have K2 times e to the minus 1 is 0.368. So that's where that kind of odd percentage comes from, that odd fraction comes from. So we know at 1 time constant, the value comes over here and hits right there. The other thing that's kind of neat about this is the tangent at this point. If I look at the tangent at this point, it actually intersects there. Okay. So this is the slope. So the slope of this curve here, the slope at that point right there comes and intersects the graph right there. That's probably not as useful as this notion here, because this is pretty nice. You go down in the lab and you measure this. You take 36.8% of it, you hit the graph here, and you have a way to measure your time constant. And you can see also that this happens again. I mean, we could do this again. This is going to be 2 time constants and then 3 time constants. And you could see when we get out to 5 time constants, that is getting pretty close to what we're going to get for our steady state answer. Okay. Now the time constant, and maybe I should go back and put that on this page here, page 3. The time constant T sub c is going to be equal to the Thevenin resistance times the capacitance, or it's going to equal the inductance divided by the Thevenin resistance. Let me double check that. Make sure that's consistent with what I'm going to do in a moment here. Yes. Okay. So very soon we're going to talk about, well, we're going to have to find our Thevenin resistance, multiply by the capacitance, or our Thevenin resistance and divide the inductance by that, and that's how we get the time constant there. So we'll be talking about all of these pieces, but I wanted to give you some general idea about this. And you could imagine if you've charged up a capacitor and then you put it in a circuit and you close a switch and you're starting to discharge that through some resistance, I think you would imagine things could decay like this. So we're going to see this kind of a shape. Well, this for some looks like it's a math lecture gone bad. Again, I'm not going to put this kind of stuff here on an exam, but I wanted you to have some idea of what's in this black box that we're going to be putting together. So for the people that don't like to think about stuff like this, we're going to move quickly now to that black box. But for others that like to know what's going on inside there, why are we doing these things, I thought this was important. So let's talk about the 6-step method. So we've got page number 5 here. And probably with this lecture, we've done a lot of math. I'll get through this 6-step method and probably just put a stop to it at that point. And that's probably not a very good place to stop, although with the videos then you can just fast forward right into the next lecture and see what we do with this. It used to be when we did this face-to-face, students then had to wait a few days, or worse yet over a weekend, and figure out how this was all going to go together, because it seemed a little daunting, a little intimidating, but I assure you, once we get into it, you might say it's tedious and long, but it's not all that difficult. And in fact, a lot of the tedium comes from, you can imagine, what we're trying to find. Where do we have that here? Back over here, R Thevenin. That's a lot of work there, oftentimes finding R Thevenin. So a lot of the tedium at this point in the term is actually almost a good thing, because we're going to practice a lot of circuit simplification, solving for Thevenin resistance, solving for voltages and currents. So we're going to try and turn it into simpler things. Maybe a bit tedious at times, but simpler things. So our six-step method, if you go through your author, many authors in this area, they have this methodology. So the first step is to assume the solution form. Okay, there's our solution form that we came up with a few minutes ago, x1 plus x2 e to the minus t over the time constant. And what are some requirements for that? It has to be an RC or an RL circuit. Okay, can't be a RCL. RCL, no, can't be that. Okay, it gets more complicated if you do that. Only a single energy storage element. Okay, only a single energy storage element. Now, if you got two capacitors that are side by side, yeah, technically you got two capacitors, but you could combine those two. So if you can combine them and come up with one energy storage element, yeah, you're good to go. But if you got a couple capacitors that are separated by sources and whatnot, you can't necessarily combine those, or you have a capacitor and inductor, all bets are off on this. You can't do it. And the source is DC. Because remember, we said the forcing function way back here, this was derived if the forcing function was a constant. So we're going to take the forcing function as constant DC. If it's not DC, you're going to have to go back to that point and start again. Okay, so those are some criteria. There's a lot of good problems fall into those. So with that, if these conditions are true, the solution is going to look like this. So then it's our task to find K1, K2, and the time constant. And the other steps here, the other 5 steps, are how we do it. So we want to assume the original circuit has reached steady state. So we haven't all of a sudden just started with this circuit. It has had time to sit there and equilibrate. It's reached steady state. And what we'd like to do is we'd like to solve for the voltage across the capacitor. Okay, so we're going to call that V at t equals 0, and sometimes I'll say even 0 minus, a little before 0, because usually at the 0 hour, when t is equal to 0, we're going to talk about throwing the switch. So if I say 0 minus, that's actually before that, okay, before the event when the circuit changes. So we'd like to solve for the voltage across the capacitor prior to that, at 0 minus, if you will, by open circuiting the capacitor. Open circuit the capacitor, find the voltage across there. Because capacitors look like an open circuit to a steady state system, right? Or we solve for the current through the inductor. This is going to be I at t equals 0 minus, for the same reasoning, by shorting the inductor. And again, inductors look like short circuits to steady state systems. So we've got this. We've got the voltage across the capacitor, or we have the current through the inductor. If we have an RC, we're doing this. If we have an RL, we're doing this. Okay? So we got those. And a lot of times what I'll do is I'll build a little score sheet, because we have lots of things to figure out in here. And I'll talk about the voltage across the capacitor at t equals 0 minus, and say that's equal to something. And because we may have several pages of work, we'll keep our score sheet here so that when we can come back to what we found here and use it to answer this. Well, let's move on to step number 3 then. And again, these look fairly daunting, like how am I ever going to remember these things? But once we do an example or two, I think you'll start to see they come fairly naturally. Again, the most difficult problem is the tedium of finding that voltage, or finding that current, or worse yet, finding that Thevenin resistance. So we'd like to 3, move or throw the switch. I don't say close the switch because sometimes the switch is already closed and we open it. Sometimes it's in one position and we move it to another position if it's like a double throw switch or something like that. So we move or throw the switch to the new position. Okay, so this is t equals 0. We were talking prior about t before 0. T is 0 minus. Now we're talking about t is equal to 0. So we replace the capacitor with a voltage source that we found in step 2. Okay, so that voltage across the capacitor that you found in step 2, we replace the capacitor with that. Or if it's an inductor, we replace the inductor with the current source that we found in step 2. And then we solve for x at t equals 0. So this might be some current or some voltage or some current. Okay, it might be somewhere else totally different in the circuit. Okay, for now we were looking at the voltage across the capacitor, the current through the inductor. Here I might be looking at some terminal voltage somewhere else, and this is what we're really starting to find now. And this is 0, time equals 0. Then between 3 and 4 we just let things go. We just wait. Okay. So at t greater than or equal to 5 time constants, this is steady state, t approximately equal to infinity, we go back. The capacitor is going to look like an open circuit. The inductor is going to look like a short circuit. So we either open the capacitor or we short an inductor because we got one or the other. This is an RC circuit. This is an RL circuit. Open the capacitor, short the inductor, and solve for x at t equals infinity. So we solve for exactly the same thing that we did up here, but now we're solving for v at t equals infinity or I at t equals infinity. Infinity being, of course, 5 time constants. Okay, so you could see now, like I'm talking about, we got all kinds of things. We've got x at t equals 0. We get x at t equals infinity. Our scorecard's getting longer and longer. So moving on to step number 5. Here's the one. With a Thevenin equivalent circuit obtained by looking into the terminals of the capacitor of the inductor. So we look into the terminals of the energy storage element and we come up with the Thevenin equivalent circuit. And this is where you really hope that there is not a diamond, right? Okay, if there's a diamond, you got to do a lot of work because you're going to have to say that what? Let me catch up on page numbering here while we think about that. We've got 5, this was 6, we got 7 up here. If you have this, you're going to have to, I maybe shouldn't have put the slash through it, it's not an impossibility, but you're going to say that R Thevenin is equal to V open circuit divided by I short circuit. You have to do both of those. If you don't have one of those, if you can do a shortcut, but if, I'm not going to say with, I'm going to say if you can use the shortcut, what do? You look back into the terminals and R equivalent is equal to R Thevenin. Okay? So this might be pretty short. If you can use the shortcut, if there's no dependent sources, you can do this. If you have a diamond, if you have a dependent source, you're going to have to find V open circuit, I short circuit. So again, more circuit simplification. And this comes at a good time in the term as people are starting to think about the final, get ready for the final. Review, node analysis, mesh analysis, circuit simplification. This can be really great review. Well, what do we do with the Thevenin resistance? Okay, we take that Thevenin resistance and we multiply it by the capacitor to get the time constant, or we divide the inductor by the Thevenin resistance to get the time constant. Okay, so now that we got the time constant, we can put this all together. This x at t equals 0 that we did in step 3, that's k1 plus k2. X at t equals infinity, that's equal to k1. So if I know k1, then I can get to k2, right? So I found k1, I found k2, and up here in step number 5, this is step 5, I got the time constant. So with that, we have finished it up. And like I said, this looks probably more daunting than it is. I'm not going to say that it's not tedious, particularly if you get in a circuit like this. You can have a lot of tedium just in step number 5. But it is also good at this point, really reinforces circuit simplification and analysis and what we've been working on all term. So if you're kind of left hanging with this, fast forward to the next video, and I'll be doing some problems that start out with some easy problems and then get into some more difficult problems that will show you how this is maybe not as difficult as it looks. Well, thank you for watching, and take care till then.